In this problem, a mechanic wrench is used to loosen a bolt at E. Knowing that the mechanic applies a vertical 100 Newton force at A, determines the principal stresses and the maximum shearing stress at point H, located as shown on the top of the 18 millimeter diameter shaft. In this problem, we want to determine the state of stress at point H here. The first step will be to see what is the resulting effect of this vertical force on this section. So first, let us put axes, x, y, and z. We can take, for example, x along this direction. So this is x-axis. This is y. And this is z. So first, this force will lead to the development of a shear in this section, a vertical shear of 100 Newton. It will also create torsion about x-axis. To find the torsional moment, all we have to do is to say that this force tends to create a moment about x. This moment is in positive x direction. So mx is like this and is equal to plus 100 Newton times the distance from A to x-axis, which is 250. Then you will get the value in Newton millimeter. And also, it's tending to create a bending moment about y-axis. So we have also a bending moment about y. It's also along positive y. So this bending moment my is equal to 100 times the distance between the force and y-axis. So equals 200 times 150. Once we determine the internal forces and couples created by this force in the desired section, we can move to the determination of the principal stresses and maximum shear stress at H. You know that the first step will be to determine for this force in the directions given in x and y, what is the state of stress. So now let us illustrate the element of interest, this top element here. Okay, if we illustrate this element, we have the following. We can draw a 2D representation of this element. This element is subjected to plane stress because it's at the free surface. Okay, so we have the following. This is our element. We have point H. Point H is the center, if you want, of this element. This is y direction. This is x direction. Now, to start with, let us find sigma x, sigma y, and tau x. Okay. First, what concerning the shear force, we know that the shear force will lead in general to the formation of shear stresses. Okay. But because point H is at the top, is at the free surface, then this shear force will not lead to development of shear stress at point H. Okay, so no shear due to the transverse 100 Newton force, because as we have seen together in this chapter, if I consider the top, okay, the top points on the free surface, Q is 0, so no shear stress due to the shear force 100 Newton at this point. Now, what is the effect of the moment, the bending moment my. Okay. For my, we know that my is a bending moment, and a bending moment results in a stress distribution. To know if this point here is subjected, this face here, any points on this face, are subjected to tension or compression, we can just say that if I consider a positive moment, so if you do with your hand a positive moment along Y, it will tend to cause tension at the upper level and compression at the lower level. So here, this side here will be subjected to tension because of the bending moment that is along positive Y. Okay, so just by doing with your hand the effect of the moment, you can see that since it's along positive Y direction, it will tend to compress here the bottom level and cause tension in the upper level. So we can say that sigma at X is the bending moment at Y times this distance times C, which is C is the radius here of the circular shaft. So times R over, of course, the inertia, the second moment of inertia about y-axis. Okay, so sigma x is m times r over I, and it's positive because it's causing tension. So now we can represent, if you want, sigma x acting on this side. So we have, until now, we have sigma x. Along y, no normal stresses. Okay, so sigma x is known, sigma y is 0. We still have to see the shear stress. Do we have shear stress effects here, tau xy? To determine this, we still need to know what is the effect of mx. Mx is a torsion moment, okay? And a torsion moment will lead to what, if you remember, we have seen together before, that torsion would lead to shear stress. And the expression of shear stress resulting from torsion is the following. So we know that from previous chapters, shear stress resulting from torsion is Tc over J, where J is the polar moment of inertia. So shear stress is not only created by shear forces, but also by torsional moments. So since here we have a torsional moment, this will lead to the creation of shear stress distribution. And the value of this shear stress is computed from tau is equal to the torsional moment times C, which is here the radius, because it's a distance from the center to the point of concern, which is here C equal to the radius, over the polar moment of inertia J for this section. So this is from this knowledge is from chapter from previous chapters, from chapter 3. Okay, so now we can say that because of the torsional moment, if I take the section and I look at the torsional moment, we have seen that the torsional moment is along positive axis. This is x-axis. The torsional moment will lead to this torsion, and this torsion will create shear at this level in this direction. So if I want to represent the corresponding shear, okay, so I have the following direction as depicted in the figure along. So we have, this is tau. created for this side. Okay, so I can now say that if I represent the shear at this level, okay, I have the following. I have for this element a stress, a normal stress, and I have also the effect of shear. Okay, so this is tau. This is tau here on this face. So tau here should have an opposite tau along this direction. And if I go to this face, I have tau like this. Okay, so in this case, I was able to determine the normal stress in X and Y and the shear stress resulting on this element. And therefore, once I represent the shear stresses acting on my element of interest, now I can say that I know the state of stress at point H for frame X and Y, and I can deduce the maximum shearing stresses from just applying formulas. Okay, so let us go again over the details. The first step will be to determine what is the equivalent action of this force at the section at point H. We have a shear of 100 Newton, as we said. We have a bending moment of 100 times 150 equal to 15,000 Newton millimeter. We have a torque of 100 times 250 Newton millimeter. This will cause, as we mentioned, bending effect. Bending will result in normal stress in sigma. So this will create sigma along X. And it is the value of this stress. First, you do the right-hand rule to know if it's tension or compression. So you depict the direction of the moment, and you will see if it will cause compression or tension. The upper level here, we found out that it's tension. And next step is to say what will be the effect of the torsion moment. The torsion moment will lead to the creation of shear stress. So since we have a torsion moment, this will lead to the creation of a shear stress on our face of interest. So we have tau equals to Tc over J, and sigma is mc over I. So we have found sigma and tau. Plus we said that because point H is at the free surface at the top, so it will not be affected by the shear. The shear force will not lead to a creation of shear stress here because it's on the free surface, and then the first moment Q corresponding to this point is 0. So the only effects created are due to the torsion and bending, and therefore we can say that at point H the effect of transverse shear is 0. So we just have the resulting stresses sigma and tau, sigma and X, and tau xy applied on this element. And therefore, once we know sigma X and tau xy, next step will be to say that I can compute the maximum stress and the principal stresses according to the formulas developed before. So first I can find the value of sigma average, which is half sigma X plus sigma Y. And also I can find the corresponding value of sigma minimum, sigma maximum, because sigma minimum is given by sigma average plus the radius, where the radius, to know it, is we just need to have the state of stress in frame xy. We have determined sigma x, sigma y, tau xy. The radius is the radical of sigma x minus sigma y over 2 square plus tau xy square. And then once we find the radius, we say that for the principal stresses, the maximum principal stress is sigma average plus the radius. The minimum stress principal stress is sigma average minus the radius. And finally, tau max is equal to the radius. And in this way, we were able to determine the principal stresses and the maximum stress on H. Let us move now to another example. In the following problem, we have a steel pipe AB that has a 102 millimeter outer diameter and a 6 millimeter wall thickness. The arm CD is rigidly attached to the pipe. We want to determine the principal stresses and the maximum shearing stress at point K. So here it's a similar procedure. Always will have the first step is to determine what is the effect of the external force on the section of interest. The section of interest is this one. We have a circular section here. And in this circular section, we are interested in particular in what is happening in the element containing point K. So first we will say that let us see what is the effect of this force on this section. And once we do this, we can determine at point K the state of stress, and then deduce principal stresses and maximum shear stress. So to start with, this force will lead to a shear force in plane XZ of the cross section. So let us represent first the cross section. We have our circular cross section. These are the axes. Here they gave us X, Y, Z. Okay. So first we can say that this force will lead in this section to a shear force, and this shear force is equal to 10 kilonewtons. Now, concerning moments created by this force. First, if as we can see, this force can lead to a bending moment about Z axis. And if you do the right hand rule, okay, you have that the moment about Z is a negative moment about Z. Okay, so I can say that the moment I have a shear, the shear is along X axis. Okay, so I have Vx equals to 10 kilonewton. I have a moment about Z axis in the negative direction of Z. So moment about Z is minus 10 times the distance from the force to Z axis, which is 150 millimeter. And also I have a moment about Y, and this moment has a torsion effect on this cross section. And this moment is along positive Y. So I have My equals to plus 10 times the distance here, which is 200 millimeters. Now, once I find the effect of the force on the section of interest, I will start to see how these internal forces and moments will affect the point of interest. So first, if I consider the element here at K, so this is my element of interest, okay? I can represent the cross section if you want again. This is my cross section. This is point K here. And I have, this is my element. Okay. I can represent my axis. So I have, this is the X axis. which is this. This is the x-axis. And I have z-axis is like this. If you want, you know that it's the case of plane stress. Okay, you can say I will name. You can consider, for example, let us say x prime y prime for plane stress. So let's say I will call this as x prime, and I can take according to general convention. We rotate from x to y prime in counterclockwise direction. So you can say that I will take y prime, which is along minus z. And I want to determine the state of stress in plane x prime, y prime. You can do this. And you can rename axis because to consider the case of plane stress. So in x prime, y prime, I want to determine the state. First, the shear along x, okay, will not affect point ky because we have seen, again, we repeat the same idea. Whenever we have a shear, the shear will lead to creation of shear stresses, but we know that V is depending on Q, the first moment. And here Q at this point is 0 because we have seen that when you do, let's say the cut, you should take the first. So for example, if you have a point here and you want to determine shear stress, you consider, let's say, this area, you find Q of this area, okay? But here we don't have, for a point on the top, Q is 0, so it will not be affected by the shear stress. So again, for Vx, no effect. Now we move to the moments, mz and my. The moment about z axis, okay, will produce what? If we go back to the figure, and we look at moment about z, the moment about z axis, this one, is a bending moment. And if you do with your hands, if you consider the direction, which is along negative z, just if you do the action of this moment with your hand, you will see that it will compress K and will cause tension on the other level. So you have compression here, compression at K, and tension at top. So here you can say that the resulting value of sigma x on K will be negative because you have compressive effect. Sorry, sigma along y axis. Here, sigma will be along y because if you look at your section is along xz plane. So when you do the effect of the bending moment will compress K, resulting in normal stress along negative y-axis depicted here. Okay, and therefore, if I consider my figure, I can say that I have compressive effect here. At point K, I have a compressive effect. Okay. Now I move to the effect of torsion. Okay. For torsion, I have also creation of shear stresses, because if I go back to the figure, this is my figure. Okay, so I can say until now I determined that bending moment will lead to compressive forces at K, at element K. Okay, and to compute the sigma compression, I just have to say that the compression state at K is the bending moment M times C over I, and C is just here the radius. Okay, and now for torsion, this force will cause a moment along this direction. Okay, so torsional effect will lead to shear stress at K in this direction. Okay, so I have then, if I plot my element here at K, if you want, if I consider an element at K, I can draw it in this way. Let's say this is the element of interest. Okay, I can plot the axis here. I have this axis, and I have this axis. So I can consider, if I want to plot x prime, y prime here, I have, this is my x prime, this is my y prime. I have compressive effects here, so I can plot sigma like this. This is sigma y prime, it's compressive effect. And I have the torsional effect. The torsional effect will lead to a shear stress here. So as you can see, this force will result in a couple along a positive y-axis, and due to this couple, due to this torsion, then you have shear stress at this element in this direction. So this is tau created at this level. So now, if you represent your element, this is your element. You have, if we consider the following names, as I told you, if we go back to x prime, y prime, because it's a 2D stress here. So we can consider that this is x prime axis. This is y prime axis. This is our element of interest. Okay. We have on this element, sigma y is negative because it will lead to compressive effects. So this is sigma y prime. And as we can see in the figure, okay, the shear on this side here, the shear on this side is along this direction. Okay, so we have this, and of course, you have on this face, tau will be opposite. So, and this is tau x prime y prime. Tau x prime, because x prime is perpendicular to this face, tau x prime y prime. And tau x prime y prime is calculated from torsion moment times c over j. J is the polar moment of this cross section. And sigma y prime, which is a compressive stress, so it's negative, is an absolute value is equal to m c over r. Okay, and here we'll put minus because it's a compressive stress. Okay, so now if you go to your analysis, the first step will be to find the polar moment of inertia, which is here. Should pay attention that I don't have a full cross-section area, because if you go back to the figure, you have like an annulus here. You have an inner radius and an outer radius. So outer radius is 51 millimeter. And the thickness is 6 millimeters, so the inner radius is 51 minus 6. You have for the formula for a annulus for the polar moment of inertia, J is pi over 2 r 0 4 minus r outer to the power 4 minus r inner to the power 4. And concerning the moment I, second moment of area about y-axis I is given by half j, which is pi over 4, r outer to the power 4 minus r inner to the power 4. So now, once we found the second moment of inertia and the polar moment of inertia about the point of and axis of interest, we can calculate the corresponding values for the shear and normal stress resulting from the internal forces and moments. The internal forces and moments created by the force applied on the system are computed as we have done together. You have the shear effect and you have torsion and bending effect. So as we said, the moment in y will lead to a torsion and then will be used to calculate the shear stress tau xy. So tau xy is Tc over J. And you have to calculate sigma y, which is, as we said, it's a compression state. So sigma y in absolute value is mz c over I. And because it's compression, it lies on the compression side. So we set sigma y equal to minus 36.56 megapascal. And then we'll be able now to determine the total stresses at point K. All we have to do is to represent K. And we say, as we did together, we take axis, if you want to not confuse with the figure, okay, to not confuse with this figure, you can use other names, okay? So this is your point K here. This is your point K. What you will do, you will take an element like this, okay? And you will say, I will consider axis, corresponding axis, in order to determine the state of stress, okay, at my point K. So I can consider, as we said, this is y-axis. Y is equal to y prime here. And we know that we have compressive effects on this side. So we say it's sigma y that I will take, then sigma y prime will be negative. And I consider the second axis, sorry. And I will consider the second axis, which is like this, x prime, to have a rotation from x prime to y prime, as we said, in the counterclockwise direction. So you can say that the x prime axis presented here is opposite to the global z direction of the frame given in the figure. Okay, so xyz is the frame given in 3D, but since you have an element and you want to compute the stresses, normal and shear stresses for this element, you can take a local frame, a local 2D frame. You can name them, if you want to not confuse with other axes of the 3D frame, name them x prime, y prime, for example. So just you have to plot your element of interest. And once you plot it, you consider two axes, x prime, y prime, in a way that you rotate from x prime to y prime into the counterclockwise direction. And you can compare these axes with the global frame. So as you can see here, x-axis is along minus z, and y prime axis is along y. And then for this element, when you plot your stresses, you can see that you have compressive stresses along y prime direction, and you have shear forces in a way that the shear is positive, because as you can see here, this is tau xy. The normal vector here is along positive x, and tau xy is along positive y. So you can say that tau xy, or let us say tau x prime y prime, is positive. It is plus Tc over J. And once you get and no sigma x. So we know sigma x prime. So sigma x prime is 0. Sigma y prime is negative because you have compressive stress and you have found the corresponding value of this compressive stress. And tau x prime y prime is determined from the torsion effect. Then all you have to do is to apply now formulas, because you have determined completely the state of stress at K. You have the value of sigma x, sigma y, and tau xy. Then you can compute what is sigma average, what is the radius, what is sigma maximum and sigma minimum. And then you can answer the question. You can get your principal stresses, and also you can get that the maximum shear stress on at point of interest K is equal to the radius R. Okay, so this is for the radius R that is computed, of course, from this formula, which is radical sigma x minus sigma y square over 2 plus tau xy square. Now, for example, if they asked you also to determine the state of stress at H, okay? If you want to determine the state of stress at H, you can say, let me plot an element here containing H. So you can work in general with several elements. You can take this element or you can take this one. But this one is easier for you. Always select the element that is easier to work with, okay? Because if you take K and you take this element here, this element there will not be, if you want, on the free surface, while this element here, these elements are on the free surface. So try to select elements that are simple to work with, and free surface elements in general are easier to work with. Okay, this is why I can consider now, when I take H, I will consider this element, and for this element I will represent what are the effects of the force acting on my system. So to start with, okay, I can say, let me select local axis for this element. So of course I can have this axis, which is, I can call it y prime, and I have this axis, which is parallel to x, if you want. I can call it x prime. And then I can represent this element in 2D and say these are y prime and x prime. And I want to see what is the effect of the shear and bending moment and torsion moment resulting from this force. Okay, so first I know that this force will lead in this section here. We have already determined the effect of this force on this section. The first effect is the shear. Okay, the shear force V. So now if I plot my cross section here, I have this cross section and I have shear acting on it. And if I want to represent H, point H is here. This is point H. Okay, and then I know that point H is located on the neutral axis of my surface. And if you remember, if you go back to the course material, okay, you know that whenever I have any surface, so here, and I want to determine the effect of a transverse force on it, all I have to do is what? So if you consider any surface with shear effect. Not in this chapter. In previous chapter, we have seen this. Okay, we have seen this in chapter 6. From chapter 6, let us go back to chapter 6 to remind you of the corresponding effects. So this chapter, if you want, is a combination of several chapters. In chapter 3, we have seen the effect of torsion, okay, on creating shear stresses. In chapter 4, we have seen the effect of bending moment in creating normal stress. And in chapter 6, we have seen the effect of, if you want, the value of shear. Whenever we have a shear force, how it will result into a distribution of shear stress. So whenever you have a problem combining